Oops. Hi guys. We'll just give it another second. Let some other people show up. How you guys doing this morning? A little bit tired after a break. Good, thanks. It was nice sleeping in for a few days. So while we're waiting for others to trickle in, let me just kind of reorient you to where we're at. This week is our last week of new material, right? Can you believe it? We're going to finish up 2.3 in the first 5 minutes or so of class. We're going to do 2.4. Okay, after I do 2.4, it's a pretty short chapter. Then I'll answer questions on homework stuff. So like 2.1, 2.2, whatever you want to have. Remember, we have a quiz this Thursday. This is our last quiz, which is 2.1, 2.2, 2.3, 2.4. Okay. I was going to start 3.2, but I think I'm going to wait on 3.2. We'll do 3.2, which is our last chapter, on Wednesday and Thursday. Okay. So we'll have plenty of time to cover 3.2. Because it's a pretty detailed chapter. We want to make sure that you guys get that. Let's see, the homework for the chapter 2 stuff is due on Thursday when we have our quiz. And I can't remember when 3.2 was set up. I think maybe 3.2 should be due on like Monday, like in a week from now. So if it isn't set up for Monday, I'll change that. I'm going to start posting solutions. Let's see, whoops. I'm going to start posting solutions to our old homework. Remember at the very beginning of our modules page, I've got like homework solutions up at the top there. So I'm going to start posting some more solutions because I did that before our midterm, and I'll start putting some more stuff up there so you guys can start comparing. Because remember, I didn't grade your homework, so I just checked to see that you made an attempt on it. So you might want that to see solutions for how do we do things. In addition to all those detailed solutions that I've been putting up all along the way. But I'm not going to move those detailed solutions up to the homework solutions. I'm just going to put the homework solutions up at the top of the Canvas page. Also, to keep a look, keep an eye out. I think probably tomorrow I'll start putting review material. This will be on next week's Canvas page, on the modules page. Next week I'll put up. Wait, tomorrow I will put up in the that little module for next week, like review materials for our final exam. I'll put up a bunch of old final exams, and the instructors for the class, we've put together sample problems for the final exam, so you guys can, I'll post that as well. You guys can take a look at those. Let's see what else. I believe our final exam is scheduled right now for the 17th of December. And I usually wait until like next week to check that. It's rare, but it does happen. Sometimes the registrar will change it to like a different day or time. So I always wait until like basically the last week of classes, which is next week. So we meet only Monday and Wednesday next week. Those are review periods. So I usually wait to check then just to make sure, because usually by next week it's stable. And I believe that the final exam is going to occur like we did with our midterm exam, where it'll be timed, right, just like the midterm was, and but it'll be 2 hours plus 15 minutes to take a picture and upload it to the Canvas page. Be very careful. I can't be as flexible as I was on the quizzes to really make sure that you get your exam uploaded within the time. I don't even know if it'll take the upload if you go over the time limit. And then also I need to confirm with the other instructors for the final exam that we can set it up with a 24-hour availability window. I'm going to be doing that this week. So as soon as I know for sure, then I will let you guys know. But let's operate under the assumption that we'll have a 24-hour availability window for the final. But I need to make sure that I can confirm that with the course coordinator and the other instructors to make that happen. And if it's different, I will let you know as soon as I know. All right, I think that's about it. Any quick questions on the administrative stuff? not homework stuff. Homework we'll do after in the second half of the class. But any quick questions on the administrative stuff? You guys all good? If you think of it later, you want to ask me like in an email or ask me in office hours or something, feel free to do that. That's fine. All right, so let's pick up where we were before, just like a week ago. So we were talking in chapter 2.3 a week ago that we left off. We have a last example, and it's based on this theorem. I just want to remind you of where we were. So let's say I've got some function, right, f of x, small f of x, and I've got a lower bound and an upper bound. Remember, we drew it out like this, right? So here's my function. My lowercase m is my lower bound. My uppercase m is my upper bound. Okay, and then my function, cruises in between these, and I'm going from a to b on some interval of x values. Okay, so let's say I want to integrate my function from a to b, but for whatever reason, my function is maybe too complex to be evaluated that way, and I can't do it. So what I need to do is I have to come up with an estimate for what that area under the curve, between the curve and the x-axis, what that area is going to be. Okay, so I'm going to use my upper bound and my lower bound, right? So if I take this rectangle, this is my upper bound area, and I take this rectangle, this is my lower bound area, and this is the area that would be my function in the x-axis. Okay, so what I'm going to do is I'm going to say I'm going to integrate my lower bound and my upper bound in the same interval from a to b, right? So I'm going to m times b minus a, and that's less than or equal to the integral of this function, which is less than or equal to capital M times b minus a. So that basically gives, right, so this is the base, this is the height, right? So we're basically taking the area of the rectangle. Why do we do this? We need techniques because we often are dealing with functions that are complex, too complex for us to be able to integrate directly using all the tools that we have. Okay, so this coming up with an approximation, an estimate, is a really important tool, right? And I can make this really pretty stringent. This is, I showed this, pretty wide margins here just so you can visualize what was happening, but you can imagine I can make this a very strict area, and maybe even I can reduce my a to b in smaller chunks and then change my upper and lower bound accordingly to get a really good estimate of what that area is between f of x and the x-axis. So we need tools in our toolkit for being able to evaluate the integral when, say, we can't do it very easily. So this is a theorem that we're working on, right? And then our last example is example 5, okay, which we want to prove this inequality. So let me just rewrite this again. So we write it a little bit bigger. So 3/4 is less than or equal to 1/2 to 2, 1 over x dx, which is less than or equal to 3. Now 1 over x dx, that's, I can actually integrate that, right? It's not so bad. So this is a proof of concept question where we can actually get the actual area between 1/2 and 2 of this function here. But we're trying to show you, some proof of concept on it. So what I want to do is I want to prove this, right? So we're going to go through and we're going to use this theorem, right, in order to prove these inequalities. So we've got this interval. So we're talking about our interval from a to b is 1/2 to 2, so 0.5 to 2. Okay, so I'm looking at the function f of x is 1 over x. So let me just draw that out. I just want to reiterate too that the sketches, no one grades the sketches. Sketches are for you to visualize what's happening. Remember, 1 over x, our rational function looks like this. So I'm going to go from 1/2 to 2. So I'm looking at essentially this area between here and here. Okay, what I'm trying to come up with. So I need to come up with, now I'm looking at, I need to prove this, but let's pretend I'm going to just write this out as m is less than or equal to 1/2 to 2, 1 over x dx, which is less than or equal to capital M. And this would be, I would need to integrate this as well. 1/2 to 2 dx, 1/2 to 2 dx. Right, so I'm kind of putting it into the format because this says prove this, and they're giving me numbers, but I'm gonna actually do it as though I don't know what these numbers are just yet, and then I'm gonna come up with my lowercase m and my uppercase m. So because how do I know? They just gave those to me, but how do I know what those are? So we're going to show how we come up with that. So I'm looking at my function 1 over x, especially on this interval, but in general, 1 over x is a decreasing function. right? So f of x is a decreasing function. And why does that matter? Because if it's a decreasing function, that means finding the minimum and the maximum value is more straightforward. If it was a function that changed values, right, but in our interval, I'd need to be able to find the minimum along that point, okay? And I'd also have to find, this is our minimum and this is our maximum. I need to find the minimum and maximum along that. So to find the minimum, right, I'm going to take my larger number because it's a decreasing function. See 1 over x. If I take my larger number and I put it in the denominator, I'll get a smaller number. To find the minimum, I'm going to use the endpoint equal to 2. So I'm going to go f of 2 equals 1 over 2. So that gives me my minimum along the interval 1/2 to 2. Okay, so that's the first one. To find our maximum along maximum, we're going to use endpoint equals to 1/2, right? Because you can even just look at the graph, right? So here's 1/2, here's 2, right? So along this interval, we're going from 1/2 to 2. So along the interval, 1/2 gives me my highest number, my biggest number. 2 gives me my smallest number, because this is a monotonic decreasing function. Like I said, if it did stuff like this, like if it changed values, I need to find what my maximum, my minimum are. Okay. So anyway, f 1/2, this is 1 over 1/2, which is equal to 2, which is our max. Okay. These go into, this is my small m, this is my big, my big M. Okay. That goes into here and here. Right, that helps me figure out the bounds. All right, so let's go ahead and do that. So I'm going to integrate 1/2 to 2 of 1/2 dx, which is less than or equal to 1/2 to 2, 1 over x dx, which is less than or equal to 2 dx. Okay, I'm using the same bounds, right? Because remember, right, I want this rectangle, so I'm going to be using the same bounds as my original integration. Okay. So when I go to do this, I'm going to say, remember how we did this? We said this was 1/2 x, and I'm going to evaluate that from 1/2 to 2. So this becomes 1/2, and I'm going to go 2 minus 1/2, which is less than or equal to my integral, which is less than or equal to, right? This is going to be 2. This is 2x from 1/2 to 2. So it's going to be 2 from 2 minus 1/2. Okay, so look at what we did. This is small m, b minus a. This is big M, b minus a, right? So then when I multiply everything out, what am I going to get? This is 3/4 is less than or equal to 1/2 to 2, 1 over x dx, which is less than or equal to, and I do this out, this is 3. Okay, so this is what we're asked to show. This is, they gave us these numbers at the beginning, and we had to show that if we followed this theorem and this idea, this is how we're going to get it. So the way that I got those boundary points is I identified, right? I identified the minimum and the maximum along this interval of my function. Okay, and I got 3/4 and 3 after I integrated it and multiplied it all the way through. Okay, you guys. And that basically ends our chapter 2.3. Okay, you guys all set with that? I'll scan in the 2.3 lecture examples and upload them later today. All right, so let's talk about chapter 2.4. 2.4 is pretty quick. It's mostly examples that we're going to be working through with 2.4. And then once we're done with 2.4, then we can go over homework problems if you guys have questions on those. 2.4. All right, so this chapter is called The Fundamental Theorem of Calculus, chapter 2.4. All right, so what we want to do, let's go ahead and talk about what's our theorem. So I'm not writing in Fundamental Theorem of Calculus, this is part 1. There's more to the Fundamental Theorem of Calculus that we'll get to in later chapters. Is that really, I'm not convinced if that's completely in focus here. There, better. Okay, so Fundamental Theorem of Calculus, part 1. So first off, we're going to assume that our lowercase f of x, our lowercase function, is a continuous function along the interval a to b. Okay, it's a continuous function along the interval a to b. And then if that's true, then we can say, if I integrate from a to b, my lowercase function f of x, right, this is a derivative. I'm going to get the big function f of b minus f of a, which is like saying I'm going to go f of x from a to b. Okay, so I get my antiderivative. I'm going to evaluate it from x equals a to x equals b. Okay, and I plug in everywhere I see an x, I plug in a b, minus everywhere I see an x, I plug in an a. And that gives me that bounds, that area under a curve of f of x and between function and x-axis along the x interval a to b. Okay, so it actually gives us an area under a curve. Okay, and maybe you're asking, like, what happened to c? When we integrate, don't I have the plus c? We can think about it. The plus c here cancels out with the plus c there. Okay, so I don't need the plus c anymore. It goes away. It cancels out when I do this subtraction. That's our fundamental theorem of calculus. Okay, f of b minus f of a, essentially. It's our first part of it. Okay, I'll let you guys finish that, and then I've got my lecture examples for chapter 2.4. Okay, so let's do our lecture examples. So calculate the area under the graph of f of x equals x cubed over 2 to 4. Okay, so what we're going to do is I'm going to go from 2 to 4 x cubed dx. Okay, when I go to do this, I'm going to do this as our power rule. Right, my exponent, I've got my power rule here. So how am I going to integrate that? I'm going to say, I'm going to increase my exponent by 1 and divide by the new exponent. And I'm going to evaluate that from 2 to 4. So what that's going to look like is 1/4, right? 4 to the 4 minus 1/4, 2 to the 4. Okay, I just plug it into my calculator to get these values here, or I can do it out, doesn't matter. And in the end, I'm going to get this is equal to 60. I have to tell you, make sure you're aware, I know that your calculators, you can plug this into your calculator and you can get out a number, which is why we require this, the antiderivative. You must show the antiderivative with the bounds on it, the bounds of integration. It's even better if you can do this as well. Okay, this is definitely required. And this is sort of mostly required. Okay, for full credit. Okay, and this is obviously the answer is definitely required for full credit. But we know that your calculator will give this to you if you just plug in this right there. But that's why you have to show this in order to get credit. We have to see that you know how to do the antiderivative. Okay. All right, let's try the second one. X to the minus 3/4 plus 3 times x to the 5/3 over the interval 1/3. So what I'm going to do is I'll set up my integral. I'm going to go from 1 to 3, x to the minus 3/4 dx. I'm using my linearity, right? So I'm distributing the integral to both terms, this term and this term. And what I'm also going to do is I'm going to take the 3 outside of my integral, x to the 5/3 dx. Okay. Now again, this is the power rule. Okay, we don't think about it, right? But watch what happens, right? So what I'm going to do is I'm going to say this is going to be minus 3/4 plus 1. Okay, minus 3/4 plus 1. This is like 1 is 4/4. So minus 3/4 plus 4/4 is going to give me 1/4. Okay, so this is going to become, and I have to divide by that. So it's going to be x to the 1/4 divided by 1/4 plus 3 times whatever I get here. So this is going to be, my power rule says my exponent 5/3 plus 1. Okay, which is, this is like 3/3. So this is a 5. So 5/3 plus 3/3 is 8/3. This becomes x to the 8/3 all over 8/3. And we're evaluating that whole thing from 1 to 3. I'm going to rewrite this, cleaning up the denominator. So if I divide by a fraction, it's like multiplying by its reciprocal. So dividing by 1/4 is multiplying by 4. There's 3 times 8/3. 3 divided by 8/3, which is 3 times 3/8, right? Which is going to be 9/8 x to the 8/3, and that whole thing gets evaluated from 1 to 3. Okay, so that looks like 4, 3 to the 1/4 plus 9/8, 3 to the 8/3. I put it in a bracket because I have to subtract out my a. So 4 times 1 to the 1/4 plus 9/8 times 1 to the 8/3. Okay. You don't really need 1 to the 1/4 is just 1. So 1 times 4, this is 4. 1 to the 8/3 is 1 plus 9/8. Okay, so then I can multiply. So 3 to the 1/4, right? 3 to 8/3. Do all those out. Okay. Ultimately, when I did this, I had to round a little bit. So this is 26.325 minus 5.125. Okay, and this was approximately equal to 21.2. Okay. Okay, but don't forget, you need this step right here. Okay, we have to show the antiderivative, or you can go right to this step. Either one of these. Okay. We need to see the antiderivative before you start jumping in to evaluate it. You absolutely cannot do this and then give me an answer and expect full credit. Maybe you'll get 1 point out of 10, say, for example. Okay. We need to see all the steps on here. That's what we're testing. All right. Secant squared. Let's talk about that. And sketch. Now, just so you know, sketches are for you to be able to visualize what's happening. We don't grade the sketches. Okay, like, you know, I like sketches because they help me think about like what it is I'm actually trying to do here, but the sketches don't get graded, just to let you know. So secant squared. So how do I plot secant squared? Why? Here's one. So secant is 1 over cosine. So in my calculator, I would do parentheses, 1 over cosine, and I would square that whole thing. And I'd plot that. Make sure you're in radian mode. So this looks like that. Okay, we're going to go from minus pi over 4 to pi over 4. But just to kind of start getting a visual of what things look like, what functions look like, okay, and how you're trying to do it. All right, so let's do this. All right, this is a derivative. Secant squared is a derivative of some function, right? This is why you kind of want to have things in the back of your mind. So this secant squared is a derivative for our tangent function. And I'm going to evaluate that from minus pi over 4 to pi over 4. Okay, so that says I'm going to go from tangent of pi over 4 minus the tangent of minus pi over 4. Right, let's think. The tangent of pi over 4 is equal to 1, right? That's when my sine and my cosine are equal to each other. So tangents minus pi over 4 is equal to a minus 1. So this is equal to 1 plus 1, which is equal to 2. Okay. Always remember, this here is a derivative of that function right there. Okay, so don't be thinking, oh, it's gonna be really complex. How do I do that? Remember, what function is gonna give that to you as a derivative? All right, this is a good one to sketch. So sine of x, I'm gonna sketch the sine. All right, so my sine is 0 here. All right, and we're going from 0 to pi, so I'm just doing this bit. Okay. All right, so what function is going to give me sine of x as a derivative? That's going to be our minus cosine of x, and I'm going to go from 0 to pi based on that here. So let's go ahead and evaluate that. Minus the cosine of pi minus a minus cosine of 0. Right, this is minus cosine of pi plus the cosine of 0 minus minus, right? So minus cosine of pi is equal to minus 1. Cosine of 0 is equal to positive 1. So this becomes 1 plus 1, which is equal to 2. So that's the area of my sine function from 0 to pi. Okay, you guys got that? We're going to contrast that. We're going to take the integral again of sine of x, but we're going to go from 0 to 2 pi. So let's draw this out. How does that look different? 2 pi. And remember, this sine function keeps going. All right, so we're going to take this area from 0 to 2 pi. That's the area that we're working. So I have an area above the x-axis and an area below. Let's see what happens when we do that. All right, so again, what function gives me sine as a derivative? That's minus the cosine of x, and I'm going to go from 0 to 2 pi. So I'm going to get minus the cosine of 2 pi minus the cosine of 0, which is minus the cosine of 2 pi plus the cosine of 0. 2 pi and 0 are actually the same angle, right? We've gone full circle around there. So this cosine of 2 pi is equal to 1. Cosine of 0 is equal to 1. So minus 1 plus 1 is equal to 0. So the area above the x-axis is equal to the area below. Okay, remember we were talking about this as a signed area, right? So you have to be careful when you're doing this, right? If I integrate from 0 to 2 pi on my sine or my cosine function, they're going to cancel each other out to get a net area of equal to 0. Okay. All right, so I've got this function here. I want to integrate from minus 0.3 to 0.6, e to the 3x minus 1. All right, let's go through our checklist of how we can integrate things, right? So it's an exponential function, right? I guess I have to ask myself, can I just integrate it normally? Can I just, e to the x, right? So if I integrate e to the x, I'm just going to get e to the x. Well, I can't do that because I've got 3x minus 1. I've got a function in my exponent, so I can't just integrate it normally. So my next check on my checklist is, can I do u substitution? So let's think about that. So my u would be this function here, so 3x minus 1. My du is equal to 3 times dx. That's actually possible. So this is going to become du over 3 equals dx. So I can substitute in my dx with a du over 3. I can substitute in 3x minus 1 with u. So u substitution will work just fine. So let's rewrite that. I have to tell you, don't put the bounds because the minus 0.3 to 0.6 corresponds to the variable x. So this is e to the u du over 3. I used to write the bounds to remind myself of what things were, and then when I went through after I integrated, I'd substitute back and I'd evaluate it. But there are some people when they grade the exams, they're very particular about this. They say, well, the bounds correspond to the variable x and not with u. So I know that some instructors will teach you how to rewrite this and basically re-index our intervals here to correspond to U. I don't follow that. I leave these things here because our original problem was in terms of X. So just leave these bounds off. We're going to integrate it. I'm going to get the 1/3 carried through e to the U. And then I'm going to substitute back in for U. So this is going to become 1/3 e to the 3x minus 1. And I'm going to evaluate that from 0.3 to 0.6. Okay. Do this here, right? Because you want to be able to evaluate your function because it was originally in terms of X. So don't worry about rewriting. If you know how to redo it, reevaluate things in terms of U and then rework it or whatever, you know, that's fine. But it's better to think about it in terms of X. So leave the bounds off. So don't do extra work, right? Evaluate it, substitute it back, and then now we can think about our fundamental theorem of calculus and plug things in. So our fundamental theorem of calculus says e to the 3 times 0.6 minus 1 minus 1/3 e to the 3 times minus 0.3 minus 1. Right, so I applied everywhere I saw an X, I plugged in my upper value, minus everywhere I saw an X, I plugged in my lower value. Okay, and then they didn't tell us, you know, leave in terms of E or anything like that, so I just wrote it out as a number. So when I did this, there's some rounding happening here. 0.742 minus 0.05, which is approximately equal to 0.692. Okay. Unless you're told to leave it in terms of E, you can come up with a number. It's fine. Okay, so U substitution worked. Don't forget to substitute back. All right, let's scroll up. So this one here, we're going to go from 2 to 8. We're going to integrate dx over x. Well, this is 2 to 8. This is 1 over x dx, which in terms of integrating is x to the minus 1 dx. We're going to sketch it out just to be able to visualize what we're doing here. So remember, a rational function, I've got asymptotes at zeros, and then my function goes like this. And then my function goes like that. So I'm going to go from 2 to 8. So I'm going to go from here to here. So I want this area under my curve. Okay. So I'm not going across, you know, some breakage point. We're going to learn in calculus 2 how we handle that. If I've got a discontinuity, what I need to do, how I'm going to integrate if I've got a discontinuity or something. We're not doing that right now. All right, so x to the minus 1. So I can't do power rule, no power rule, because of my exponent. If I do the power rule, I'm going to bomb out. So remember, 1 over x integrates as the natural log. Don't forget your absolute value. Okay, when you are taking the absolute, when you are taking the natural log, you have to put the absolute value on there. And I'm going from 2 to 8. Okay. So this I'm going to evaluate as the natural log of the absolute value of 8 minus the natural log absolute value of 2. I'm being a stickler about it and showing that I'm plugging it in. Okay, but technically speaking, I don't need to anymore because both 8 and 2 are positive. All right, which is going to, I can do this. I can say natural log of 8 over 2, which is the natural log of 4. Natural log of 4, which is equal to approximately 1.39. Okay, that's my area under the curve here from 2 to 8. Again, we're doing the same function here, right? Except now I'm going to go from minus 4 to minus 2. Minus 4 to minus 2, x to the minus 1 dx, right? So I'm going to go from right there. So this is kind of like our signed area, right? We're talking about a function, part of our function is below the x-axis. Okay, so the same process holds true. Okay, x to the minus 1 integrates as natural log of the absolute value of x, and I'm going to evaluate that from minus 4 to minus 2. Okay. Right, which means I'm going to go natural log of the absolute value of minus 2 minus natural log of the absolute value of minus 4. Be careful, don't get confused, right? Minus 4 is smaller than minus 2. Okay, sometimes, and I say that You roll your eyes, you think, I'll never get confused, but you're going really fast, you're on an exam, you're on a quiz or something like that. Just keep that in mind. Always be thinking about what your bounds are here. So I'm going to plug them in. So this is the same thing as the natural log of 2 minus the natural log of 4, right? Because we took the absolute value of it, which is the natural log of 2 over 4, which is the natural log of 1/2, right? Which is approximately equal to minus 0.69. I say approximately because I'm rounding a little bit, right? Minus, right? Because it's assigned area. We're beneath the x-axis here, so it's negative. But if I forgot my absolute values, right, I would have bombed out. How do I take a natural log of a negative number? Remember, this is a good clue, okay, that I need to be mindful. When I take the natural log of a function as a part of the process of doing the integral, I must put the absolute value on it. Okay. You guys, that actually wraps up chapter 2.4. That's it. I will scan in these lecture examples later today and then post them to our Canvas page. The lecture examples for 2.3 I'm going to post to last week's Canvas modules page, because that's where we had posted the lecture example for 2.3. So keep an eye out for it there. 2.4 will go on this week's. Okay. All right. So that's it in terms of lecture stuff. I am open to answering questions about homework if you guys would like to ask. 2.1, 2.2, 2.3, I think we have. You can ask about 2.4, although I think probably haven't started it yet. Let's see. Hang on a sec. Let me get out my. Somebody did start 2.4. Good. All right. Let me get out my work solutions for 2.4 as well. Give me a sec. Right. So we'll start in order here. What was the first one? 2.1, number 12 and 19. 2.1. Yeah, let's do subchapter 2.1, question 12. So question 12 is funny. Let me write down the problem first, and then k equals 4 to 8, k minus 3 squared minus j equals 1 to 5, 9j plus 20. So, the point is, like, we want to be able to, these are small ranges, 4 to 8 and 1 to 5, they're small, but think about it as like, 4 million to 8 million, or 1 million to 5 million. I mean, you like, we can enumerate these because there's only a handful of them, but like, let's think about if they were much bigger. So the thing that we want to be able to do is, our goal is to be able to combine these into one summation so that I can reduce the amount of computations I need to do, right? So what I'm going to do is, I'm going to readjust the indexes, right, so that they overlap better. So we can combine some terms. Okay, so I can combine these into one. So that means I need to readjust. I'm going to readjust this one. Okay, so if I readjust this one, so I'm going to go, so k equals 4 to 8, k equals 4 to 8, to go from 1 to 5 is what I want, right? So to do that, I have to subtract 3. So if I subtract 3 from 4, I'm going to get 1. If I subtract 3 from 8, I'm going to get 5. So if I subtract 3, that's going to help me readjust my indexes. So that means I'm going to go k equals 1 to 5, right? This is going to look like k plus 3 minus 3 squared. And that minus j equals 1 to 5, 9j plus 20. Well, now that they have the same summation bounds, I can combine them into one, right? So this is going to look like k equals 1 to 5, k plus 3 minus 3 squared, minus 9, k plus 20. They can have the same letter now because they're like part of the same summation, right? Because they have the same index, so I can lump them all into one. Watch out for the sneaky little minus sign, because that minus is going to go to both of these terms here, okay, when we go to subtract it. So you're going to FOIL all this stuff out, right? And then combine it with 9k plus 20. And what am I going to get? I'm going to get k equals 1 to 5. And this is going to be k squared minus 9k minus 20. Okay. And now I can actually just enumerate, right? There's only, 1 to 5 terms on here. It's, it's pretty short enumeration, but imagine if I had like more terms, and then we wouldn't actually ask you to enumerate more than just a handful of terms. But if I had more than that, I'd write like a program to do it. And you can do that even in Excel. Okay, so it's going to be 1 squared minus 9 times 1 minus 20, just to show you what it looks like. K equals 1, k equals 2, 2 squared minus 9 times 2 minus 20, k equals 3, k equals 4, k equals 5, and then I get minus 180 as my summation. Okay. 12 and 19. 19. Okay. Okay, give you guys a minute to write that down. Okay. All right. So chapter 2.1, question 19. All right, so this one says calculate delta f of k when f of k equals 3k squared minus 4k plus 7. So there are a couple ways to think about it. I'm going to do a couple different things. So what this is like, let's think about it. I'll go like this. So delta f of k equals f of k minus f of k minus 1. Okay, this is like comes from our book, but basically how we get delta f of k minus f of k minus 1. So I'm going to plug in, this is my 3k squared minus 4k plus 7 minus f of k minus 1. So wherever I see, this is going to be k minus 1 squared minus 4 k minus 1 plus 7, right? So wherever I saw a k in here, I plugged in a k minus 1. Okay, now I get to FOIL this out and combine all the like terms, right? So this is ultimately gonna, it's just sort of lots of algebra. Lots of algebra, and I'm gonna get 6k minus 7. And you can show the algebra if you want. You should show the algebra. I'm skipping it just for now. 2.4, question 41. Chapter 2.4, question 41. All right, so it says, what is the derivative of 0 to 3x 3t dt? Okay, so first off, I'm going to take this integral, I'm going to evaluate it from 0 to 3x. So let's pretend I don't have that first. Okay, so if I just do this integral part first, okay, so I've got 3 as a constant term. I increase my exponent by 1 and I divide by that. I'm going to evaluate it from 0 to 3x, okay, which is going to give me 3 halves 3x squared minus 3 halves 0 squared, right? I just did my fundamental theorem of calculus. Okay, so this is going to give me 3 halves times 9x squared minus 0. Okay, so this is going to become 27 halves x squared. Okay, so this is what I get here. Now I'm going to do the derivative part. So I'm going to go dx of 27 halves x squared. Okay, so now I'm just going to take that derivative, which is equal to 27 over 2, my constant term, times my power rule 2 times x to the 1, right? I subtract 1 from my exponent. So this is going to be equal to 27x. Take it in steps. Um, 2.2, number 37. Okay. Chapter 2.2, question 37. All right, so we said, so we're given f of x equals x squared, and we're going to go from 0 to 1. So our partition setup is 0, 1/4, 1/2, 3/4, and 1. And our sample set, 1/4, 1/2, 3/4, and 1. Okay. So now what I'm going to do is I'm going to say W. That's going to equal to this times F 1/4 plus F of 1/4 plus F 3/4 plus F of 1. And I did that because, right, these were all just spaced by 1/4 apart. Okay, so I could do that way. I like, because the delta x was like consistent, it was the same, so I just factored it out. So this is 1/4 times 1/16 plus, I squared it, right? 1/4 plus 9/16 plus 1, which was equal to 15 over 32, which was approximately equal to 0.46875. Okay. 2.2, number 20. Scroll up. All right, so 2.2, number 20. We're looking at from t equals 0 to t equals 90 seconds. We're inflating something, and then we've got want to know what is the total volume of air at t equals 90 seconds. Okay, so we're given, I think, the rates of change. So from 0 to 20, our change in volume over time is equal to 2 cubic inches per second. You guys will have this 37. I'm gonna do this. Okay, and then we're gonna go from 20 to 50. Our change in volume over time is equal to 5 inches cubed per second. From 50 to 70, like our rate is changing, right? Is equal to -3. We lost a little bit. 75 to 90. Our rate of change is equal to 4 cubic inches per second. Okay, so now we want to be able to figure out the total volume of air. So the volume is going to equal to the rate 2 times the time differential, right? dV dt. So I multiply it. This is going to give me my volume plus 5 times 50 minus 20. So I get the 5 from here, 50 minus 20, plus I'm going to get the -3, 70 minus 50, plus 4 times 90 minus 75. So I add them all up, multiply them out. I'm going to get my total volume was 175 cubic inches. Okay. you guys think of other questions, I have office hours today. The homework for this is due on Thursday, right? So 2.1, 2.2, 2.3, 2.4 is all due Thursday midnight. So if you haven't started it yet, please start taking a look at it right now. 2.9, question 29, sure. And then, like I said, I think our chapter 3.2, I think should be due on like Monday, but I'll go check that again. Would we say question 29? Okay. All right. You guys will have this here. I'm gonna get rid of this. All righty. So this is chapter 2.1, question 29. So what is, we've got j equals 17 to 25, radical j minus radical j minus 1. What is that equal to? So, you know, it's not too big of a number, not too big of a range, 17 to 25, that I can actually just come up with it. But what I'm going to do is I'm going to show you a trick just a little bit, just so you can see. So I'm going to start enumerating a little bit. So radical 17 minus, right, this is j minus 1, radical 16 plus, right, so this is my j equals 17. My next one around, radical 18 minus radical 17 plus radical 19 minus radical 18 plus so on and so forth until I get up to, you know, 25. But watch what's happening. This is what's called a telescoping. We're going to be dealing with a telescoping series in calculus 2. So this is kind of like we're giving you a preview of coming attractions here, because watch what happens. This one, radical 17 cancels out with minus radical 17. They cancel. So I can go like that, right? And then this 18 is going to cancel out with that 18. Those cancel. And then I'm basically going to get this one here. And then my very last one is not going to be canceled out. So at the very end, so I'm going to get radical 25 minus radical 24, right? So then what will happen is 24 will cancel out and I'm left with 25, and then I'm left with this one. So I'm left with the very first one and the very last one. Okay, so I've got basically a radical 25 minus radical 16. Okay, so this becomes 5 minus 4, which is equal to 1. Okay, it's a telescoping sum. We're just trying to get you to think about what these things look like. If you were to have enumerated this out all the way from 17 to 25, it's not very big, right? You could do it, right? It's not a very big amount of terms to do. You'd still get, like, you just subtract it out each one and then you add them all up, you'd still get this equal to 1 at the end. But it's good to start to kind of enumerate these things to recognize what the pattern is, so you can cancel out all the duplicate terms. And what you're left with is this one and this one. And then they just become the final things that you add together, essentially. And what we get is 5 minus 4. Okay. But you weren't expected to recognize all that. You could have just enumerated it and got the same answer. Okay, but we just wanted you to kind of get a feeling for it, because you will be seeing this type of thing next semester. Okay. All right, guys. If you don't have any more questions on the homework problems, or if you want to ask them in office hours, which I have today, or if you want to ask them on Wednesday's class, we can. Anyway, then I'll let you guys go early, and I hope you have a great day. Take it easy.
Thank you.
Thank you.
Bye.
Thank you.
Take care.
Thank you.